Okay, this is Dr. Brown. In this video, we are going to be talking about monotonic functions and the first derivative test. And these tests are going to allow us to tell whether a function is increasing or decreasing and help us find maximum and minimum points on a function. Let's first of all look at some definitions. Let's say that we have an interval and x1 and x2 are on the interval and x1 is less than x2, and if f of x2 is greater than f of x1, the function is said to be increasing. That's pretty obvious on that interval. Now, if x1 is less than x2, but f of x2 is lower than f of x1, then we say that f is decreasing on that interval. Now, here we see the function y equal x squared as an example, and we see that on the first interval here the function is decreasing, and notice that the first derivative is less than 0. So if the first derivative is negative, the function is decreasing, and if the function is increasing, as you already know, the first derivative has to be more than 0. Now, for the function f of x equal x cubed minus 12x minus 5, we want to identify what we call critical points. Critical points, as you remember, are where f prime is equal to 0 are not defined. So let's calculate f prime for this function. The derivative is defined for this cubic function for all value of x, so there are no points where the first derivative is not defined, but let's see if we can find where it is 0. The first derivative is 3x squared minus 12 equals 3 times x squared minus 4 equals 3 times x plus 2, x minus 2, and it is equal to 0 when x is equal to minus 2 and when x is equal to plus 2. So it's 0 at these points. At all other points, the derivative will either be positive or negative, so we want to divide the timeline to intervals between these points where the derivative is 0. So the first step you're going to do when you're looking at the intervals where a function is increasing and decreasing is to just look at all these critical points and divide up the number line between minus infinity and the first 0, which is minus 2, and then between minus 2 and the next critical point, which is plus 2, and then between x equal 2 and infinity. And to see whether the derivative is positive or negative, we need to pick a test point. And so we need to take a test point on the interval that we're concerned with, and I would usually pick the one that's the easiest to evaluate. For the first interval, I would pick -3. For the next interval, I would pick 0. For the next interval, I would pick 3. And we want to test f prime at the test point and look at its sign. So f prime at -3, looking at what f prime is, would be 3 times -1 times -5 equals 15. This is more than 0, so the function is increasing. Now let's look at the test point of 0. The first derivative is 3 times plugging in 0 in the first derivative would get 2, and -2 equal -12, less than 0, so it is decreasing. And then finally we look at first derivative at 3 to see what its sign is, and we get 3 times 5 times 1 equal 15, more than 0, so it's increasing. So now we know the intervals without even graphing the function on which the function is increasing and decreasing. If you then go and look at the function, this is a graph of f of x equal x cubed minus 12x minus 5. And indeed, we see that the function is increasing between -infinity and -2, and it's decreasing between -2 and +2. And then on the interval +2 to +infinity, it's again increasing. So here the first derivative has told us whether the function is rising or falling. In fact, this graph is just an example of some possibilities that you will see, and we want to say that for functions, the first derivative tells us how the graph rises and falls. In this particular graph here, you see the first derivative is 0 at this point. And before that, f prime is more than 0, so the function is increasing. First derivative is obviously 0. At this point, f prime is more than 0 between here and here, so the function is increasing. First derivative equals 0 at this point. Between these points, f prime is less than 0, so the function obviously is decreasing. and at this sharp point, f prime is not defined. You see, in this example, it's happens to be an absolute max. Between this point and this point, the function has a derivative more than 0, so it's increasing. And then at this point, f prime equals 0, obviously. In between, f prime is less than 0, so it's decreasing. And notice it doesn't have to decrease and then increase. In this last interval, f prime is also less than 0, so it continues to decrease. Notice on this particular example, the first point is an absolute minimum. The last point is a local minimum. That is, it's lower than any other point in the vicinity. Now, we're going to talk here about the first derivative test for local min and max. I've got 3 examples. In each example, right at the middle, f prime is equal to 0, f prime equal to 0, and f prime equal to 0. Now, to the left of the first function, f prime is more than 0, in other words, it's increasing. And to the right of the f prime equals 0, f prime is less than 0, so it's decreasing. So if you have increase, then a decrease, you have a local max. You could draw yourself a little diagram, increasing, decreasing, and say that's local max. In the second example, we have f prime is less than 0 and know that it's decreasing. Then on the other side of the critical point, f prime is more than 0 because it's increasing. So if we have a decrease followed by an increase, we have a local min. And then finally, it's obvious this test shows us if we have an increase followed by an increase in which the first derivative is more than 0, we have a not an extrema, not an extreme point. And you could also show that if you have a decrease followed by a decrease, that you have no extremum or no extreme point. So this is the first derivative test for local min, local max. Now we have another example here in which we want to find the critical points of this function. Notice it's a mixed function with a polynomial and an exponential function. We want to identify the intervals on which f is increasing and decreasing and find the function's local and absolute extreme values. Well, the first thing we need to do is find the first derivative. The first derivative is going to be the first, which is x squared minus 3, times the derivative of the second, which is just the derivative of e to the x is e to the x, plus the second, which is e to the x, times the derivative of the first, which is 2x. Simplifying this, we can pull e to the x out and get e to the x times x squared plus 2x minus 3, and set this equal to 0. Notice e to the x is never 0, and we can factor x squared plus 2x minus 3 into x plus 3, x minus 1 equal to 0 at x equal minus 3 and x equal 1. So these are the critical points. And to find the intervals on which the function is increasing and decreasing, we again need to set up the intervals between minus infinity and the first 0, which is minus 3, between minus 3 and the next 0, which is 1, and between 1 and plus infinity. And now let's pick test points. For minus infinity to minus 3, the easiest one to do is probably minus 4. For minus 3 to 1, the easiest is 0. And for x between 1 and infinity, I would pick 2. So now I'm going to write down f prime is equal to e to the x times x plus 3 times x minus 1. Notice this is always, e to the x is always going to be positive, and we need to plug in the test point in these factors here. So the sine of f prime at minus 4 is going to be, first of all, plus. That's the e to the x. It's going to be plus. Plug in minus 4, and we get a negative sign. Plug in minus 4 here, and we get negative sign. So that is two negatives, and they multiply together to give a positive, so we know the function is increasing between minus infinity and minus 3. So now we want to find the sine of f prime at 0. It's going to be a plus again, and then the sine of 0 plus 3, which is plus, then the sine of 0 minus 1, which is minus, so that's less than 0, so the function is decreasing. Finally, we're going to plug in x equal 2 and calculate the first derivative at 2, and we get a plus for e to the 2. We get a plus and a plus, which is more than 0, so it's now increasing. So now we can graph this function and see, just as we calculated, that between minus infinity and minus 3, it's increasing. This is a graph of the function. And between minus 3 and plus 1, it is decreasing as predicted. And between 1 and infinity, it's again increasing. Now we're going to work more problems like this in the classroom. We're going to work one more problem, and this example, why don't you ignore the fact that I have repeated this question. I'm not going to go back and take this off right now. We want to find the critical points of this function x to the 1/3 times x minus 4, which is equal to x to the 4/3 minus 4x to the 1/3. Let us first calculate the first derivative of x, which is going to be 4/3 x to the 1/3 minus 1/3 times minus 4 is minus 4/3 x to the minus 2/3. So we can factor 4/3 x to the minus 2/3 out, and we're left with x minus 1. And we set this equal to 4 divided by 3, and we put x to the 2/3 on the bottom to make it a positive exponent times x minus 1. And this is equal to 0 at x equal 1, and it's undefined at x equals 0. Notice if you plug in x equals 0, the derivative is undefined, so a critical point where the derivative is undefined is x equals 0, and the other critical point where the derivative is 0 is x equal 1. So now we need to look at f prime equal 4 times x minus 1 over 3 x to the 2/3 power. And we need to look at x between minus infinity and the place where it's undefined, which is 0, and between x equals 0 and x equal 1, and then finally between x equal 1 and infinity. And we need to pick test points. Test point I would pick on the first interval is minus 1. For the second interval I would pick a half, and in the third interval pick about 1.5. And now let's look at the sign of f prime. At minus 1, you can see that we're going to have f prime at minus 1 is going to be 4 over 3 times minus 2 minus 1 to the 2/3 power. The numerator is going to be negative, and the denominator, which would be the cube root of minus 1, which is minus 1, and then square minus 1 is going to be positive. So on the first interval, this is going to be less than 0, a negative over a positive, so it's going to be decreasing. Now plug in L prime at 0.5, and you can see we're going to get 4 times minus a half divided by a positive number at the bottom when we plug in 0.5, and so it is again less than 0, so the function is still decreasing. Then finally, when you plug in 1.5, you're going to get 4 times 0.5 divided by 3 times 1.5 to the 2/3. That's going to be obviously positive, so it's going to be increasing. So on the next page, we have a graph of the function x to the 1/3 times x minus 4. As you can see, the tangent line at x equals 0 is vertical. It's undefined. It's approaching infinity. We see decreasing as expected from minus infinity to 0, and still decreasing between 0 and 1. And then finally, between 1 and infinity, it is increasing, just as the first derivative predicted. And that is monotonic functions and the first derivative test.